I'm working mostly on the hardware optimizations, so I am counting CPU ticks that it takes to solve different problems. And a couple of years ago, I have stumbled upon very interesting algorithm that allows me to compute sliding window sums. You can think about sliding window sum as you have an operation that I denote by this plus in a circle. It could be just arithmetic addition, it could be real plus. In this case, the operation that we are computing is sliding average with a certain window. Another good example that I originally stumbled upon was a sliding maximum operation. Again, you have a long array of data, you select a subarray, you calculate a maximum. You slide your window by one, you calculate a maximum again, and so forth. Using the notice of the prefix sum, you can create an interesting and parallel algorithm. First, let's think about the case where the data from your long array comes one by one as scalars. You have a vector that contains partial sums. You take a new data point, you broadcast it in your array, you add it to the partial sum vector, and you get one complete sum that you push out, and you also slide the vector by 1 point. Now you're ready for the next step. So this algorithm is very easy to comprehend. There is not much parallelism. So let's try to improve it. Now you are taking your data points by a full vector. So if your architecture allows vectors of size n, you take n new points. You calculate suffix sums, creating your partial sums that are very similar to the previous step. And you create the prefix sums with the new data. Then you add your prefix sums to the suffix sums of a previous step. You get a lot of output, the full array, and you're ready for the next step. The paper actually describes also some improvements to this algorithm, but this is the crux of it. By using prefix sums, you can compute them in parallel. So this algorithm is very fast in practice. Some things you could improve if you can see by calculating suffix sums, you're not using the full vector. There are some zeros in this vector, which means in reality that you're not using your vector architecture to the full capacity. You can overcome these limitations by a little more complex algorithms. You can see that the description of an algorithm, you have a sliding window that rolls across an array and you do some computation, is actually very similar to the fundamental operation of a convolutional neural networks, because when you compute a convolution, you have a filter that you slide along a layer and do the convolution operation. So it looked originally that convolution is a very good candidate for this algorithm. The problem is I didn't know how to represent a convolution as a prefix sum. It took me just 3 years. And here is the formal application. So the one step of a convolution is a dot product of two vectors. First, I do a little manipulation with the vectors to eliminate zeros. This is the formal mathematical definition. When I code, it is actually just masking. It doesn't require any operations. And after you removed zeros from your two arrays that you will do dot product with, you create a new sequence of pairs and you define the new operation, this plus in a circle, and you can prove that this operation is associative. So the dot product is actually representable as a prefix sum. Awesome. What are the results? I have coded the 1D convolution and compared the convolution speed to the one in Onyx framework. It is an open source framework for AI operations. It is used by Azure ML. That's why, as a Microsoft, I have access not just to the source code, but to the people who wrote it. And they were really helpful in explaining me how everything works. But as you can see, I can achieve a substantial speed up with different kernel sizes. And the speed up is approximately proportional to the logarithm of a filter size for the convolution. There is another interesting coding problem that I'm still working on. Since this has been coded in AVX 512 for the single precision floats, a single vector contains 16 floating point numbers. For the vectors of longer size, I create a virtual vector by logically combining several hardware vectors. This allows me to process vectors of substantial length. And the convolution kernel of size 17 could be processed by either kernel, either single vector or multiple vector kernel. And as you can see, multiple vector version, the fused line, shows a little bit better performance. So I'm still trying to understand what causes the orange dot to be more performant and how they bring the blue dot up. And does it mean that I bring not just the dot for the 17 kernel size, but the whole blue line could be moved up, achieving greater performance? I spent some time analyzing what is the reason for the speed up, because even though some operations could be performed in parallel, the number of operations, the number of multiplications performed in convolution does not change. Compared to the standard methods of performing convolutions that reduce it actually to the matrix multiplication. And the motivation is very simple. Matrix multiplication has been the focus of computer scientists for a very long time. The very efficient routines for matrix multiplications exist for any architecture, including some typical IoT devices, which means either DSPs, digital signal processors, or some small ARM processors. So converting convolution to the matrix multiplications works really well. Why I'm doing better? It looks like sliding sum approach. First, it works on original data representation as compared to the matrix multiplication approach that actually performs very well-known IM to call operation that increases the data representation in memory. And second, sliding sum algorithm accesses memory in a very predictable pattern, which makes the CPU work for accessing memory very predictable and easy. So this is the roofline analysis of 1D convolution. The big red dot is the Onyx framework matrix multiplication kernel that actually performs all the required convolution operations. And the green dots are the loops that use sliding sums. You can see that they're all aligned along the DRAM roofline, which means the performance is limited only by the DRAM speed. But the bigger the kernel size, the filter size, the more is compute to memory ratio, and the better is performance. And if you move further along, so to the kernel size 51, and it is actually the real life example of using 1D convolution. It is used in RNA analysis neural networks. You can see that now I am bound only by hardware limitations. So I am processing math as fast as possible. The same is true for 1DNN. That is actually the default convolutional framework, say, behind the TensorFlow. You can see that their kernel is pretty much at the same point. And a little peek into the future, if you implement the 2D convolution, my kernels are actually not bound by DRAM. They are efficiently accessing memory and now limited only by cache performance compared to the matrix multiplication algorithms. So this is the key for success of these sliding window algorithms. They do the same number of multiplications, so they're doing the same arithmetics, but they're accessing memory in a very efficient way, which also makes them competitive with the GPUs now. Because in my opinion, the key to the GPU success is the explicit control of different levels of memory caches. If you want to follow the updates on my work, 2D convolution and more experiments, you can look at GitHub. Onyx Runtime is an open platform, and I am checking in updates regularly. So welcome, use it, test it, find more applications. I think it's even more valuable in the Internet of Things space, where you always do not have hardware or economic budget for different convolution accelerators. So it means your CPU could now perform convolution very efficiently. Thank you. Any questions?